We will start the session now at 6 p.m. Okay. Good evening to all, and welcome to the problem solving session for week 10 for the NPTEL course Heat Transfer with course ID noc24-ch17. My name is Nidish V, and I will be your teaching assistant for today. Okay, today we will be discussing some questions for the week 10 topics. These are the week 10 topics. We had 5 lectures pertaining to radiative heat transfer. For the first lecture for the weeks, it was discussion on properties of a black body. Professor used Planck's law, Stephen Boltzmann used Planck's law to derive Stephen-Boltzmann's constant in this lecture. Wein's displacement law and the band emission were discussed in this lecture. In the subsequent lecture, the properties pertaining to radiation from real surfaces was discussed, and the wavelength and directional dependence of this emission from real surface were also discussed. In lecture 48, the energy balance for quantifying radiation exchange in an enclosure is presented, and the properties of gray surfaces and associated quantifying aspects were also discussed. In lecture 49, the talk on radiation exchange was discussed. The importance of view factors in radiation exchange was discussed in these lectures, and the method for finding view factors and various rules pertaining to the view factors were discussed in this lecture. In the last lecture for this week 10, that was lecture 50, several examples for estimating view factors for various geometries were presented. These were the 5 lectures that we had on radiative heat transfer in this week for the week 10, and now we will discuss some problems, about 5 problems today pertaining to these topics. So before beginning this session, it is expected that everyone has gone through these 5 lectures, and with that we will begin the problem solving session for this week 10. Let me go to the first problem. I will read out the problem for you. A small surface of area A1 equal to 10 power minus 3 meter square, that is this surface at the bottom, is known to emit diffusely. This is an emitter and it is emitting diffusely. And from measurements, the total intensity associated with emission in the normal direction is IN equal to 7000 watts per meter square steradians. Radiation emitted from the surface is intercepted by 3 other surfaces of area A2 equal to A3 equal to A4 equal to 10 power minus 3 meter square, which are 0.5 meters from A1 and are oriented as shown in the figure. What is the irradiation at surfaces A2, A3 and A4 due to emission from A1? That was the question statement. Take a minute to go through the question statement. After that, first we will discuss the question statement, then we will proceed to solve this problem. Take a minute to go through the question statement and let me know if there is if something is unclear. Okay, first let's discuss the question. There are 4 surfaces given to us, and the area of these 4 surfaces are given. Actually, all 4 of these surfaces A1, A2, A3 and A4, they have the same area, 10 power minus 3 meters square, and among these A2, A3 and A4 are placed at a distance of each at a distance of 0.5 meters, same distance but at different orientations from surface A1. And among this, surface A1 is an emitter of thermal radiation, and it is emitting thermal radiation diffusely and from some measurements the intensity of normal total intensity of normal radiation in the normal direction from this emitter is also given as 7000 watts per meter square steradians, and this radiation is being intercepted by surfaces A2, A3 and A4. And now we have to find out the irradiation at these surfaces due to the emission from the surface A1. That was the question part. Have you solved problems similar to this during the lectures? Okay, if not, let's I think proceed to solve this problem. Okay, say there is an emitter, some emitter, and there is some receiver. Okay, emitter say surface 1 and some receiver X. It could be 2, 3 or 4 in our case, surface 2 or surface 3 or surface 4, and surface 1 is the emitter. So what is the expression for irradiation? Say I want to find out irradiation G due to the emission from surface 1 to surface X. That means surface 1 is emitting some radiation, and out of that what is being intercepted by the surface X. X in this case being either 2 or 3 or 4. We can say it is the total heat transfer rate associated with this emission divided by the surface area of the receiver, right? This is the irradiation, incident heat flux on surface X from the radiation due to surface 1. Okay, so now what we can do is we can actually expand this, the denominator, let me keep it as it is, area of surface X, and the numerator, that is the heat transfer rate between surfaces 1 and surfaces X, can be related to actually the intensity of emission, the surface area of the emitter, the angles between these two, and the solid angle between these two. We can use all these quantities to express the heat transfer rate between these two surfaces. So this heat transfer rate Q1x can be given by the intensity of emission from surface 1 multiplied by the area of surface 1 into cosine of the angle at surface 1, that is cosine of the angle means this theta 1. First we have to make a normal to this surface 1, then we have to connect the both the surfaces. Theta 1 would be the angle between these two. Okay, this is the emission part. Now it is being intercepted by the surface 2 with a solid angle of say omega x1, where the solid angle omega x1, sorry wx1, can be given by as the ratio in terms of the area of the surface X receiver, that is AX multiplied by cos theta 2 or cos theta x by r square, where r is the distance between these two. Okay, now what is the theta x in our case? This theta x would be the angle between the normal to this x surface and the line joining these two surfaces, right? So with that information, let me rewrite this expression for irradiation G1x, that is irradiation due to the emission from surface 1 that is intercepted by surface X, equal to I1 A1 cos theta 1 multiplied by the solid angle is given by this expression, ax and ax from the numerator and denominator will cancel out. Remaining we have cos theta x divided by r square. So this is the expression that we need to solve our problem. This is cos theta 1. Okay, if it is confusing, this is cos theta 1, this is cos theta x. And let me know if what theta 1 and theta x is in our case. Is that clear? Let me know if this part till now is clear for the audience. This is an expression for irradiation on surface X due to emission from surface 1. Is that part clear?
Yes, sir.
Okay. Then please note down this expression and we will go back to our previous slide to look at our geometry. Now what we have to find out is, first we have to find out irradiation due to emission from surface 1 to surface 2 equal to, then irradiation from surface 1 that is intercepted by surface 3 equal to something, and irradiation from surface 1 that is intercepted by surface 4 equal to something. In all these cases, do we know I1? I1 is the
7000 watt per meter square.
7000 watt per meter square steradian is the emission in the normal direction, right? Is emission in other directions the same for this case?
Sir, 10 to the power minus 3 meter square. No.
No, actually, yes, you are right. The normal intensity in normal direction is given to us. Intensity of emission in normal direction, yes, it is given to us. It is also given to us that this surface is emitting diffusely, right? That means it would have the same intensity in all angles. Irrespective of the direction in which it is emitting, it will have the same intensity of emission, right? That is the meaning of diffuse emission. Is that clear? That is clear, right? Jitendra? That part is clear, right? Why we can take this normal intensity as same as I1 in this case, because in whatever, if you want to look at the radiation emitted to A4, maybe we have to look for the intensity of emission in this direction, but it is given to us that this emitter is emitting diffusely, so it is emitting with the same intensity in all directions, so we can use the same value for this emission, right? Yeah. So can you, A1 is known to us 10 power minus 3 meter square. Cos theta 1 is known to us, like cos theta 1 and cos theta x depends on the pair, which pair we are considering. Are we considering emission from A1 that is being intercepted by A2, or are we considering emission from A1 that is being intercepted by A3, or are we considering emission from A1 that is being intercepted by A4? And R is the distance between these two surfaces. So can someone tell me for G12, for G12, what is the value of theta 1? G12 means emission is from A1 and interception is by A2. What is the value of theta 1? Theta 1 is actually the angle between the emitter and receiver at the near the emitter surface. Angle between the normal direction to the emitter and the angle between the line joining the emitter to the receiver. So what would be theta 1?
30, sir.
60. Theta 1 is near the emitter part, right? We are
Yeah,
interested
yes, sir. Yes, sir. 60, sir.
we are interested in this angle, the angle near emitter, and that angle is measured in between this normal direction. This is the normal direction to A1, right? Angle between this and the line joining emitter and receiver. The angle between these two red lines.
Yes, sir. Correct, sir.
So theta 1 equal to 60 degree. And what would be theta x? That is theta 2 in this case.
45.
Theta 2 would be, no. Theta 2 would be the same angle near
30,
receiver.
30, sir.
30 degrees, yes.
Yes, sir.
Now what is R?
0.5
0.5
meter.
meters, right? And you have value for I and you have value for. Can you please show the previous explanation slide once? Okay, I will go to that slide. Give me a moment. You have values for R and you have values for I and A1. With that, start calculation. Do this calculation. Substitute all these values in this radiation expression and find out the value for G12. Okay, here is the slide, Bala. So G12 would be 7000 this is what we get, right? Have you calculated this value? Okay, I will also try to calculate this value. 7000 multiplied by 10 power minus 3 multiplied by cosine of 60 in degrees. Okay, make sure you are calculating in degrees, multiplied by cosine of 30 degrees divided by a1 square, 0.5 square, not a1 square, r square, the distance square. So the value we are getting is 12.12, right? Are you getting the same value? Okay, 12.12. Before that, what would be the units for this? It would be watt per meter square, right? It is irradiation flux. Bala, this is the problem statement slide. You wanted to note down? Okay. Were you getting the same answer? Now we need to calculate G13, that is the radiation that is emitted by A1 and that is intercepted by A3. Notice that these two surfaces are facing each other. They are 90 degree opposite and facing exactly each other with the same area. So can someone tell me what would be theta 1 in this case and theta 3 in this case and r in this case? Can someone tell me what would be the value for theta 1?
Sir, R will be 0.5, theta 3 will be 90, theta 1 I am not sure, sir. 60?
Why theta 3 would be 90? Be careful what angle you are measuring. These angles are the angle between first the normal line.
Theta 1 is 0.
0, right? What about theta 3? Theta 3 also would be 0, right?
Yes, sir.
They are facing opposite to each other because the angle that we are measuring is the angle between the normal to the surface, that is this. This line is the normal to the surface, and the line connecting these two surfaces, that is the same line, right? Both lines are same. So the angle between these two are 0, right?
Yes, sir.
Yes, sir.
That is clear, right? Make sure you are taking the right angles for calculations. So we can, is this part clear? Why theta 1 and theta 3 are 0?
And both facing each opposite to each other, sir.
Yes.
Exactly opposite.
Yes. And for G14, theta 1 equal to the angle between normal and the line joining these two, 45 degrees. I'll write down.
45 degrees.
What would be theta 2? Not theta 2,
That
theta
is
4.
0.
Theta 4 would be,
That is,
any guesses on what theta 4 would be? Not guesses, any?
that would be also 45.
Theta 4. Notice that this theta 4 is the angle between the normal to the surface. This is the normal to the surface. Let me try. This is the normal to the surface. And the line joining this surface and this surface. Both are same surface, right? No, both are same lines, right? Is there some confusion? Okay, let me draw it here.
Theta 4.
My pen is not working.
I think theta 4 equal to 0, sir, right?
Which one? Yes, yes, right. Did you
Theta 4 is going to become 0, right, sir?
Yes, yes, it will be 0. You now understand how it comes, right? I'm sorry, I'm facing some technical issues. Okay. Theta 4, is it 0? Yes, it is 0. Theta 4 will be 0. Give me a moment. Is there some lag from my side? Hello? Can you hear me?
Yes, sir.
Okay. Actually, my system started hanging. Give me a moment.
But your screen is visible, sir.
Okay, okay, okay. Then it should be fine. Full screen. Let me check if the recording is still on. Yeah, everything is fine. So, okay, I'll write this theta only for G14 case and then we will proceed. G14 theta 1, we said that it is 45 degree. Theta 2, not theta 2, theta 4, we said that it is 0 degree. I hope it is and everyone understood why it is theta degree. Sorry, 0 degree. And r is 0.5 meters. This is what we have. So I will let's substitute all these values in our equation and get the final results. For G13 it is 7000 into 10 power minus 3 into G13 is 28. Yes, that is correct. Cos 0 and cos 0, right? It would turn out to be 28 watts per meter square. Can you similarly find G14? Cos 0 divided by r is same in all the cases. R equal to 0.5. and if you do this calculation you will get a value of around 19.8 watts per meter square. Okay, I hope this calculation is understood by everyone. Let me again give you how theta is calculated. Say if this is surface 1 and say if this is some surface x. First we have to draw normal line to these two surfaces. Say this is normal and say this is normal to this surface. Then we have to join the centers of these two surfaces. Okay, then theta 1 would be this angle and theta x would be this angle. I couldn't draw it properly, but I hope you understood how we calculated this theta 1 and theta x, right?
Yes, sir.
Okay, so if this is clear, shall we move on to the next problem?
Yes, sir.
Okay, this is problem 2. Let me read the problem statement. A furnace with an aperture of 20 millimeters diameter and emissive power of 3.72 into 10 power 5 watts per meter square is used to calibrate a heat flux gauge having a sensitive area of 1.6 into 10 power minus 5 meter square. At what distance measured along a normal from the aperture should the gauge be positioned to receive irradiation of 1000 watts per meter square? Here consider theta f and theta d equal to be 0 degree. This is what is given in the question. Take a minute to go through the problem statement, and after that we will discuss both the problem statement and the solution. G13/28 G, yes. Okay, is the problem statement clear? We have a furnace, that is this furnace that is shaded by this red that I am marking in the figure. We have furnace with an aperture of 20 millimeters. It has a diameter of 20 millimeters. Okay, and this is emitting some thermal radiation with an emissive power of the emissive power E is given. Note the units. Previously we were given intensity with units of watts per meter square steradians. Now the emissive power of the surface is given in units of watts per meter square. The emissive power of the surface is given to be 3.72 into 10 power 5 watts per meter square. Okay. Now we have a detector, or in this case a heat flux gauge, and it is having some area 1.6 into 10 power minus 5 meter square. It is at a distance of L from this furnace. This is the thermal radiation source, and now this detector is the thermal receiver, radiation receiver in our case. Both of them are positioned at a distance of L, and they will have some angle, just like how we found earlier. They will have some angle. Say the angle at here would be, say it is theta f, and the angle here would be theta d. Even though it is shown like this in this figure, having some angle theta d, but in the problem we are being asked to find out, consider theta f and theta d as 0 degree. That means just like they are facing each other. This is what we have been given. and the problem is we need to find out at what distance this detector should be placed so that the radiation that is received by this detector equal to 1000 watts per meter square. That is the problem statement. Let me know if it is clear.
Yes, sir. Proceed.
Okay. How can we solve this problem? We can use the same equations, right? In the first problem also we had an emitter and we had receivers and we knew the intensity of emission and all, right? Let's write the equation that we had in problem 1. Say irradiation that is emitted by furnace, in this case furnace is emitting and some detector is detecting, equal to Q furnace to detector divided by the distance, not the distance, divided by the area of the detector. Okay, again we can write the same thing. This is intensity of emission from the furnace multiplied by area of the furnace into cos theta of the furnace with the solid angle omega detector furnace divided by area of detector, right? Now this we can expand as intensity of emission from the furnace multiplied by AF, this is same, into cos theta F, same, and the solid angle can be written as, how can we write the solid angle? Area of the receiver, that is detector, multiplied by cosine of the angle at the detector divided by the distance square, right? Whole divided by AD. Okay, now AD and AD will cancel out. Is this much part clear? This is the same as what we did in problem 1, just that I am changing the, earlier I wrote I think 1 and x. The first letter here is the emitter and second letter is the detector. The furnace is emitting some thermal radiation, F denotes furnace and D denotes detector. Okay, so AD and AD will cancel out, and area of furnace we have, theta of furnace we have been asked to take it as 0, theta near the detector we have been asked to take it 0, L we have to find out, so that is an unknown. Okay, GFT is the thermal irradiation that is intercepted by the surface D, that is detector. Due to radiation from surface F. that is the furnace. That is what GFD is in sentence. What is actually GFD represents in sentence by the surface of receiver. Terminal radius that is entered by the surface D. Yes, detector in this case, like, yes, D is the receiver, this is the receiver, and this is the emitter. In this problem, it is being called just furnace and detector. That is why I kept the naming like that. Is that clear? Okay. Now IF, intensity of emission from the surface furnace, is not given to us directly, but we have learned that intensity of emission can be written as, if we know the emissive power, it can be written as emissive power divided by pi, the hemispherical solid angle, right? This is known to us, so we can substitute for IE as this E by pi in our expression. So ultimately it just boils down to GFT equal to E by pi into area of furnace into cos theta furnace into cos theta detector divided by L square. Okay, now we can just substitute all values in this, because this irradiation is what we know actually. In previous case, this is what we had to find out, but in this problem it is known to us that the surface should get an irradiation of 1000 watts per meter square. So that to get this much irradiation, what should be the value of L? At what distance the detector should be placed so that the detector can receive that much irradiation. When the detector is close to the receiver, it will receive the maximum, it will receive some irradiation, and when it is at a distance R, the irradiation received would change, and this depends on L. This L value, this is inversely proportional to this L value and directly proportional to the area of cross section and this cosine of angles between them. So let me substitute these values. This is 1000, I think. We need 1000 watts per meter square irradiation, and E is given to us as 3.72 into 10 power 5 watts per meter square. By pi, and area of furnace. What is the area of furnace? Okay, wait, did we miss something here?
Area is given in the problem.
Area is given, right? Okay. Area of furnace, where it is? Okay, diameter is given to us, so we can calculate the area of furnace.
Sir, the sensitive area 1.6 in 10 to the power 5 minus 5 meter square.
That is not furnace, that right? That is detector, right?
What is, sir? What?
Area of furnace would be this, pi into d square, this one, 20 mm. Pi into mm square. Pi d square by 4, right? Yeah. Area of pi d square by 4. Then what value should theta f is 0, given to us as 0, 0. theta d is given to us as 0, and L is what we have to find out. Let me know what answer you are getting. How much are you getting? 0.386 meters. Let me check. .386, not 0.386, right? 0.192, yes. 0.192 is the correct answer. Did you not take a square root earlier, or yeah? So it means that if the detector is placed at this distance from the source, it will have received a thermal radiation of 1000 watts per meter square. That is what this means. That is what this problem was asking us to find. Forgotten to divide by 4. Okay, pi d square by 4. Yeah. Okay. Yeah. Take a minute to go through the solution and let me know if the solution part was clear. Problem 3 in assignment 10. Actually, we are not supposed to tell solutions how to solve assignment problems, but again, I have not seen assignment problem. Problem 3 in assignment 10. I will check the problem and I will get back to you. Actually, can you drop your email ID or email ID in the chat window? I will check the problem and I will see how it is. Problem 3 assignment 10. Okay, actually we are not supposed to discuss assignment problems, but I will see what it is about and I will give you what is the approach that we can use to solve it. Okay, yeah, I will give you how we can proceed. Yeah, okay, I will check the problem after this session and I will give you how we can proceed to solve it. Problem 3 in assignment 10, right? Okay. Okay. Other than that, I hope this problem was clear, right? Yes. Okay. So shall I move on to the next problem? Okay. This is problem 3. Let me read out the problem statement. Consider a metallic surface with measurements of the spectral hemispherical emissivity yield a spectral distribution which may be approximated as follows. Okay, and one spectral distribution of emissivity is given. Determine the corresponding values of total hemispherical emissivity epsilon at 1750 Kelvin. Have you already previously seen problems like this during the lectures? where you have been given a spectral distribution of emissivity and you are being asked to find out total emissivity. Have you solved problems like this in this lecture, in this course? Okay, I think I don't know if professor had already explained it. Okay, but first let me explain this plot. On the x-axis we have the wavelength at which the thermal radiation is being emitted, wavelength lambda in micrometers. We have 0 micrometers, 1, 2, 3 and 4 micrometers, extending to higher values also, wavelength. And on the y-axis, on the vertical axis, we have the corresponding emissivity for each wavelength. And we can see that for radiation between 0 to 2 micrometers, the surface, the metallic surface, has an emissivity of constant emissivity of 0.36. And after that, from 2 to 4 micrometers, the surface has an emissivity of 0.2. And for higher values of wavelength, the emissivity is 0. This is what is given to us. And from this spectral emissivity, this is like emissivity corresponding to different wavelengths. Now we have to find out total emissivity. What would be the total emissivity corresponding to all the wavelengths at a particular temperature 1750 Kelvin. Now how to solve this problem? That is our question. Take a minute to go through the problem and let me know if the problem statement is not clear. Is the problem statement clear? Yes. So we can proceed to solve this problem. Okay. We have been given spectral distribution of emissivity and we need to find out the total emissivity. Now, how can we find out this total emissivity? First, what is this emissivity? How emissivity is defined as? Emissivity is defined as the emissive power, emissivity say for a given wavelength is defined as emissive power corresponding to that wavelength divided by emissive power of a black body for that wavelength. Right? This is the definition of emissivity. That is, or it can also be said that emissive power is equal to emissivity times the emissive power of black body. Both are same definitions. Okay. Now, we need to find out the total emissivity. That is epsilon over all the wavelengths. That we can write as similar to this, a ratio of emissivity at different wavelengths. So we have different wavelengths and so we will just integrating from 0 to infinity. This is integration over the wavelength. The emissive power at different wavelengths can be written as E lambda is equal to epsilon lambda into EB lambda, right? Emissivity at that wavelength multiplied by emissive power of black body at that wavelength into D lambda divided by this denominator. emissive power of black body. Total emissive power of black body averaged over all the wavelengths. This is our expression. Let me know if that is clear, because we will now proceed to expand it for our given problem. Okay, now we can expand it. Can you please explain this equation once? Is this one is clear, right? The one in the square bracket, this is the definition of emissivity. Emissivity equal to emissivity equal to emissive power of a gray body or a real body divided by emissive power of black body. From that, now just come to this equation. Emissivity is again, the numerator is emissive power of a real body, and denominator is emissive power of a black body. Total emissive power and total emissive power. Denominator is black body, numerator is real body. How is emissive power of a real body defined? It is epsilon times the emissive power of a black body, right? Since this emissivity is not a constant throughout the wavelength, we have to integrate it over the complete wavelength range. That is why we are for each wavelength we are multiplying this emissivity corresponding to that wavelength multiplied by emissive power of black body at that wavelength, and integrating for all the wavelengths, so that the numerator finally turns out to be E lambda, not E lambda, emissivity of the actual. This is actually E by, this is just an expression for emissivity is equal to E by EB. This is what is written, just E is expanded in this form, like emissivity into emissivity of emissive power of black body. Is that clear? That is clear. Okay. Now let us expand this for our given problem. We need to find out the numerator. For the numerator, let's go to this expression. When lambda is going from 0 to 2, the emissivity is a constant value of 0.36. From lambda, when lambda goes from 0 to 2, emissivity is equal to 0.36. And when lambda goes from 2 to 4, the emissivity is 0.2, and when lambda greater than 4, emissivity is 0. This is clear, right? From the given spectral distribution. Now we can rewrite this as an integral form. We can plug these values in the integral that we wrote on this slide. So this top part integral can be rewritten as, when lambda goes from 0 to 2, the emissivity was 0.36 multiplied by emissive power of black body into d lambda, plus when lambda goes from 2 to 4, the emissivity was 0.2 multiplied by emissive power of black body d lambda, plus above 4 it is 0, right? Total emissivity is integral over 0 to infinity of monochromatic. Yes, right. That is right. That is what we are doing here. it's also the ratio of total emissivity of monochromatic radiation from a real body to that ratio of total total emissivity of radiation over all the wavelengths from a black body divided by EB. This part is clear, right? Then how we got that multiplication of EB lambda? These B and lambda are subscripts, okay? It is E subscript B lambda, just to indicate that emissive power of a black body at a wavelength of lambda. What is this is emissive power of a black body, right? At a wavelength lambda. Is that clear? And what do we get when we multiply emissivity at a wavelength lambda with this quantity? We get the emissive power of a real body at wavelength lambda, right? Yeah. So the ratio what we want is emissive power of real body divided by emissive power of black body, right? Numerator is the emissive power of real body and denominator is the emissive power of black body. Is that okay? Okay. Now this can be rewritten as 0.36 is a constant. Let us take it out. 0.36 into integral 0 to 2 EB lambda d lambda divided by EB plus 0.2 integral 2 to 4 EB lambda d lambda by EB. This is clear, right? I just rewrote the integral taking constants outside and dividing separately by EB. Now these quantities, this integral of EB lambda over certain wavelength divided by total emissive power of black body, this ratio is known as black body radiation functions. Black body radiation functions. Denoted by capital F. So I will rewrite it as 0.36 into black body radiation function from wavelength 0 to 2 micrometers plus 0.2 into black body radiation function for wavelength 2 to 4 micrometers. I can rewrite it like this. And people have already tabulated these values for different black body radiation functions corresponding to different temperature and wavelength of emission. Okay, so on the right hand side you can see a table where there are two columns. Left side is value of lambda t, which is given given in the units of micrometers Kelvin, and on the right hand side column we have corresponding black body radiation functions. Please note that all the black body radiation functions are given for emission from 0 to lambda. So we have to rewrite whatever expression we have in terms of 0 to some quantity lambda. So what we can do for that is 0.36. We can rewrite this expression as 0.36. This quantity is blackbody radiation function from 0 to 2. So there is no need to rewrite that. Plus 0.2 multiplied by this quantity is from 2 to 4. We can rewrite that quantity as difference between blackbody radiation function from 0 to 4 minus blackbody radiation function from 0 to 2. This quantity is same as this quantity. The quantity between the square brackets is same as F24. Let me know if that part is clear. Yes. So now we can now we have to find out this F02 and F04. If we find out this F02 and F04, we can directly substitute that in this and get the total emissivity. Now, how to calculate F02? Let's go to this table. We have been given F02 lambda. So, lambda for F02 case is 2 micrometers. Corresponding to that 2 micrometers, what is the lambda T value? That is what we have to find out. The T here is the temperature. Remember that in the question, we have been asked to find out the total emissivity at a particular temperature, 1750 Kelvin, right? So that is the T value. So for let me write it here due to lack of space. For finding out F02, lambda T is equal to 2 micrometers into 1750 Kelvin. That is 3500 micrometers Kelvin, right? This is the lambda T corresponding to this F02. So for 3500 micrometer Kelvin, let's see what is the F value. 3400 is here, 3500 is here. Now if we take the average of these two values, we will get the corresponding value for 3500. So if we take the average of these two values, we will get it to be 0.361735 plus 0.403607 by 2. We will get 0.382 382671. Yes, actually these values will go in increasing order. When lambda T is small, F would be small, and as lambda T approaches higher and higher values, this value will approach 1. So actually when lambda T is very high, this value would be close to 1. This F value actually indicates here, this is the F value, right? F value actually indicates out of the total emission from a black body, what is the contribution by different wavelengths. That is what is indicated by this F value. How much is, say, 0 to 2 micrometer emission contributing for the total black body emission corresponding to this temperature. That is what this 0.382671 represents. Now we have F02. Also we need to find out F04. For F04, what is lambda T? Again we have to calculate lambda T because lambda is different here. Lambda is now 4 micrometers. Sorry, lambda T is 4 micrometers into 1750. that is 7000 watts per 7000 micrometers Kelvin. Okay, now we need to find out the blackbody radiation function corresponding to 7000 micrometers Kelvin, that is this value. So F value is 0.808109. So we can finally substitute, we got all the values that we need. We can finally substitute all these values in our equation and get the total emissivity. F02 was 0.38267 and F04 was 0.808109 minus 0.38.2228. Okay, yes, I think that is correct. Yes, 0.382671. So when we do this calculation, we will get the total emissivity as 0.22. Yes, that answer is correct. Now we got the total emissivity of the surface for which the spectral distribution was given as 0.22. This is how we solve these kind of problems using the input from blackbody radiation functions. Take few minutes to go through the solution and let me know if there was some part that was not clear. If you want, you can go back to the question also. I think it was clear. Is the question and solution clear for everyone? Was there something that was not clear? Yes. Yeah.
Yes, sir. Proceed, sir.
Okay. Then we can proceed to our next problem, problem 4. Let me read out the problem statement. An enclosure has an inside area of 100 meters square. An enclosure has an inside area of 100 meters square, that is AS, and its inside surface is black and is maintained at a constant temperature. Okay, there is an first let's read the question. A small opening in the enclosure has an area of 0.02 meters square, that is A0. The radiant power emitted from this opening is given to us as 70 watts, that is Q radiated. What is the temperature of the interior enclosure wall? This is the problem. Take a minute to read the problem again, then we will discuss it. Okay, what we have is a an enclosure, say some enclosure with a small opening. The small opening, say this is some small opening, and it is given to us that the inside surface is black. Enclosures with small opening, actually we can consider them to be as black bodies. Was this mentioned in lecture note or lectures? This is AS and this is A naught. This small opening is A naught. Okay, such enclosures with small opening, we can consider them to be as black bodies, because whatever radiation that is entering this enclosure is assumed to be successively reflected and absorbed by this enclosure body. So its emissivity is absorptivity is assumed to be 1, and emissivity is it's assumed that it will absorb all the incident radiation and it will be a perfect emitter. Such enclosures with small opening are considered to be black bodies. So whatever the radiation, so whatever the radiation that is emanating from A naught will be similar to a black body radiation. That is the key to solving this problem. Go through the problem and let me know if the problem statement is clear.
Yes, sir. As emitting from this hole, how much intensity of the heat it is going out, that with respect to temperature inside. So we need to find out the temperature inside, sir.
Yes, right. Once we identify that it is an equivalent black body, it is a simple problem. The area outside is A naught, area inside is AS. Say that temperature inside is, say it is TS. Then it behaves like a black body with a surface of A naught. Whatever emission emanating from A naught will be equal to an emission from will be equivalent to an emission from a black body. So the total radiation emitted from this A naught surface will be equal to that area A naught multiplied by the emissive power of a black body at a temperature of Ts, which is equivalent to this temperature. So that can be written as A naught into emissive power of a black body, Stefan Boltzmann constant into Ts power 4. Is that clear? Once we identify that this can be considered as a black body, then the problem turns out to be very simple. Even though it is a surface AS that the enclosure is having, the final radiation is considered to be emanating from this small opening A naught. So we will consider A naught as a surface that is emitting as a behaving like a black body. That is the concept. Okay, so you already solved it. Let me write the equations. Q radiated equal to 70 watts. So you can write 70 is equal to A naught is 0.02, and what is the value for Stefan Boltzmann's constant? 5.67 into 10 to the power minus 8, right? Watts per meter square, Kelvin power 4 into Ts power 4. and we need to find out TS. What value did you get? 298, 498.5, 498.45. Yes, that answer is correct. You will get a value of 498.5 or 45 something. If we consider why are we not considering the area of the enclosure in this case? Do you have any thoughts on that? Because if you see this figure itself, you will get an idea about that.
Sir, because from that opening, radiation depend on the temperature.
Yes, okay. See, whatever radiation that is being emitted from this opening is already contained all the radiation that is coming from here, and make sure if this is the opening, the radiation that is emitted from this opening is going outwards, right? But what about the radiations from these surfaces? It is going in all directions, and these radiations are again striking here, and these radiations are again striking here. So when we consider this area for emission, radiative emission, it is like whatever radiation emitted is getting reflected here, again it is getting reflected here, it is getting reflected here. Finally whatever comes out is through this opening, and that is the final radiative power of this black body. And for that we will consider this area of opening. When we consider radiation from this area of opening, that actually is equivalent to all the radiative emission emanating from this enclosure black body surface. Because if we consider this area, the radiation emitted from this angle is also intercepted by the same area, right? So it becomes complicated. Actually, these all will come in view factors. If we multiply it by area of enclosure, what we get? I don't know if there is some physical interpretation for that, for the answer that you will get, because whatever radiation that you are calculating that way will be like, it will be a cumulative effect of all the reflected radiation, and all is included in that. I don't know if there is a separate physical interpretation for that, but it would be wrong if you want to calculate this emissive power from this enclosure by that way, because as I already told you, this emission is not only propagating outside, it is also being received by this surface itself. Have you learned about view factors in lectures? View factors represented by F11, F12. Is this part already taught? It would be the total energy emitting from the enclosure, but most reincident there itself, and only that calculated value may. But when you are taking area of enclosure, it is considering all that reincident radiations also, right? My point is, when we are taking the area of only the opening, we are considering only the radiation that is coming out of this black body. But when we are taking area of the enclosure inner surface, yes, when we are taking enclosure of inner surface, it is having like additional, it is emitting radiation, but that same surface is receiving that radiation also. So it is like we are unnecessarily computing the radiation emitted plus the radiation received by itself also. Is that clear? Is what my understanding is okay. It would be total energy emitting from the enclosure. The radiation what we want to calculate is total energy emitting from the enclosure. Yes, but total energy emitting from the enclosure is being emitted by this small opening, and whatever the energy that is being emitted from that small opening, it is propagating outside the enclosure. It is not getting again absorbed by the enclosure, it is propagating outside, so that is emitted. But when we take inside area is also emitting radiations, but the same area is receiving that radiation. So when we take inside area, yes, it is emitting radiation, but it is absorbing that same radiation. So it is not the, we can't say it is the emitted radiation from that black body. Most inside in there itself, and only that calculated value may come out from the opening. Yes, if we take a naught, the small opening, only that calculated value will come out of the black body enclosure. Yes. Yeah. Is that okay? Okay. Is this part already taught in lectures, view factor? If not, probably I think it will be taught soon also. During that time, we will see radiation exchange between different surfaces. At that time, actually, we can see when radiation is emitted by one surface and it is being received by the same surface, how we can do calculations in such cases. Okay. So yeah, I think this part is clear. If so, we will proceed to the last problem for today. That is problem 5. Let me read out the problem statement. An electrically powered ring-shaped radiant heating element is maintained at a temperature of T hot Th equal to 3000 Kelvin and is used in a manufacturing process to heat a small part having a surface area of AP equal to 0.007 meter square. The surface of the heating element may be assumed to be black. For theta 1 equal to 30 degree, okay, this is theta 1, this is theta 1 and this is theta 2. For theta 1 equal to 30 degrees and theta 2 equal to 60 degrees, L equal to 3 meters. What is L? L is this distance, okay. L equal to 3 meters and W, the width of the ring, equal to 30 millimeters. What is the rate at which radiant energy emitted by the heater is incident on the part? Take a minute to read the question again. After that, we will discuss both the problem and the solution. Okay, we have a ring shaped heating element, that is this part, ring shaped heating element, that is powered by some electricity, and it is a heating element, and it is emitting some radiation at a temperature 3000 Kelvin. Okay, now this thermal energy, heat energy, is used to heat a part that is at the bottom shown here. It is used to heat a part. The orientation of the ring shaped object, and the part that is being heated is shown by different angles. 30 degree, 30 degree, 60 degree, different orientations are shown. The distance between this ring shaped object and the area of this part and the width of the ring shaped object are all given to us, and we have to find out what is the heat transfer rate between these two, heater and part. This is what we have to find out. Is the problem statement clear? Okay, if you are reading the problem, let me know once the problem statement is clear, so that we can proceed to the solution part. Is there some confusion in the problem statement? Shall I proceed, or is something unclear? Is someone there? So okay, I'm assuming, since there is no response, I'm assuming that the problem statement is clear, and I will proceed for the solution. Okay, we have to, again here we have to find out the heat transfer rate, Q. Again we can, this is very similar to the first or second problem that we solved, where we expressed this heat transfer rate from emitter to receiver, or in this case the heater to part, as the intensity of emission from the heater into area of heater into cos theta heater into the solid angle between part and heater divided by area of part. No. Divided by area of part was for irradiation. Now we are just writing, yeah, only this part is enough. Okay. This equation is okay, right? We have seen this equation in first problem and in the second problem. Now let's see each of these individual quantities. Let's see if we know these quantities. What is IH? IH is the intensity of emission from the heater. right? Let's see if that quantity is given to us directly. Electrically powered heater, intensity is not given to us, but what is given to us is the temperature of the heater is given, and it is given to us that the surface of the heating element may be assumed to be black. Okay, now we have already seen that we can rewrite intensity of heater as equal to the emissive power of blackbody heater body at blackbody at heater temperature divided by pi, right? So emissive power of blackbody given a temperature is given as sigma T power 4. Sigma T power 4 by pi. This we can calculate. Let us check first what should be the units for this. Q should be watts. Give me a moment. Q should be watts. Area of hot body is meter square. Cos theta. This is radians. So this is watts per meter square radians. Okay, so I should be in units of watts per meter square radians. When you do this, you will get units of watts per meter square radians. Yes, right. So can someone tell me what is the value of IH? By denominator not written area. No. This expression we have seen, right? Intensity of emission can be written as emissive power of blackbody divided by the solid angle, total hemispherical solid angle. This is an expression that we have seen earlier, and I think this expression professor might have already discussed in class. This is standard expression. Area, if at all we had to include, we should include it in the numerator, right? Oh, here by denominator area. Is that what you are asking? Okay. Here we were including the denominator area when we were saying GHP, irradiation. For irradiation, it is heat transfer rate divided by area. But here we are not interested in irradiation. We are directly interested in the numerator part, heat transfer rate, because that is what is being asked us in the question. What is the rate at which radiant energy is emitted by the heater is incident on the part, that is QHP. We want only QHP, we don't want the irradiation. If we wanted irradiation, yes, we should divide by area of the part. But in this case, since we don't want irradiation, we just want the heat transfer rate, there is no need to divide it by the area of the part. Is that clear? This is not flux, this is heat transfer rate between these two objects. Yes, right. Because in this problem we are being asked to find out heat transfer rate. What is the rate at which radiant energy emitted by the heater is incident on the part? If we were being asked to find out irradiation, yes, we should divide by area. You are right. But in this case, we are not asked irradiation. We are being asked to find out heat transfer rate. Let's calculate this value. (5.67 into 10 power minus 8). That is the Stephen Boltzmann constant. divided by pi multiplied by 3000 power 4. 1.46 into 10 power 6. Yes, right. So 1461901, right? Or 902 with units of watts per meter square steradians. Okay, this is intensity. Now what is AH? Area of the hot surface. How can we find out area of the hot surface? Is it directly given to us? Area of hot surface is not directly given to us, but we have some quantities by which we can find out the area of hot surface. Area of hot surface can be written as this width into multiplied by this circumferential area, approximately width multiplied by circumferential area, that is pi d, if this is d, right? Like the circumferential area into width will give the area of this ring, that is width multiplied by pi into, but again diameter of the ring is not given, but we have been given this length L, so this would be L sine theta, right? L into sine 30 degree. With that we can find out the area of the heater ring. So I'll rewrite it here. Pi d into W pi into L sine 30 into W pi into what is L? L is 3 meter and width is 30 millimeters. Check if this expression is okay. If so, we will calculate this value. 3 pi into sine 30 multiplied by 30 millimeters. Is this clear?
Yes, sir.
Okay. And now we have intensity, we have AH. Now we need cos theta H. Let's again go back to the problem. What is cos theta H? Cos theta H is the angle near the H hot plate. It is the angle between the normal to the hot plate, that is this normal. This is normal to the hot plate, this dotted line, and the line that is connecting the center of these two surfaces. We can see that both those lines are same, right? So can we say theta H equal to 0 degree? Do you agree on that? this line is actually the normal line also, and this is also the line connecting the senders of this emitter and receiver. Because why is this normal line? If you check this angle, this is 60 degrees. If you check this angle, this is 30 degrees. So 60 plus 30, it is 90 degrees. And so this is a right angle, right? That part is clear, right? So we can see that the line joining the senders of these two emitter and receiver itself is the normal of the emitter. So since it is the same line, please explain in detail. Okay, let me try to draw it here. We have a receiver here, okay, and we have our ring shaped object here. Ring shaped object here. Okay, now we have been given that, okay, this is normal to the receiver surface, and this is the line connecting normal to the receiver surface, and this is the tangential line for this normal to receiver surface, which is given to be intersecting at an angle of 60 degree, and this is given to be 30 degrees, right? This is given to us in the question. Okay, so if this angle is 60 degree and this angle is 30 degree, this angle is clearly 90 degrees, right?
Yes, sir.
Yes. Now when we say we want theta h, this is h and this is p. When we say we want theta h, it is the angle between normal to this h. Normal to h, this h is again this line. This is the normal to h line. Angle between this line and the line connecting this hot surface and this part, again that is the same line. So it is the angle between the same line, that is 0 degrees. Is that clear? Actually the normal of this hot surface is pointing to the path, that is why it is at 0 degrees. The normal direction and the line joining, okay, say if the surface was like this, if one surface was like this, and if one surface was like this, we could say that the angle between normal and the angle between line connecting centers, we could say that this is theta h. But in this case, this ring is oriented in such a way that its normal itself is this line, so the angle is 0 degree. Is that clear? Okay, right? Jitendra, is that clear? Okay, I think it is clear. So theta h, cos theta h equal to cos of 0 degree is equal to 1. Now what quantity is remaining? The solid angle is remaining. How did we write solid angle earlier? It is the area of part multiplied by cos theta of part divided by the distance square, right? Now area of part is given to us. Area of part is 0.007 meter square, 0.007 meter square into cos of theta of part by L square. L is also, I think, given to us 3 meters. Now what is this theta angle corresponding to this part, this receiver? Can you say what theta P is from the explanation that we had? We had been calculating this theta for different geometries now, right? Theta P means the angle between
30 degrees.
what?
30 degrees.
30 degrees, yes. Theta
Yeah,
P is
30 degrees, sir.
yes, theta P is 30 degrees. Theta P is 30 degrees. That is the angle between normal to the P surface, that is this, and the line connecting the emitter and receiver. It is the angle between these two, that is given to us as 30 degrees. Yes. So this is cos 30. So that value would be 0.007 into cos 30 divided by 3. Not 3, 3 square, right? Divided by 3. So it is 0.0674. 0.0674. Only those many zeros. What was the area again? Area of the part is 0.007, right? 0.007 into cos of 30 divided by 9. It will be 0. A small value, right? 0.00067. I am getting this value. Is this correct? Or is my calculation wrong? No, I think this is correct. This is correct, right? Bara 0.00067. Yes, okay. Now we have all the quantities which we can use to, yeah, thank you. Now we have all the quantities which we can, okay. Oh, is it 0.3? Let me confirm. Length is 3 meters. No, it is 3 meters, not 0.3 meters. Okay. Now we have all the quantities that we can substitute in our heat transfer rate equation, and we can finally get the final desired answer by multiplying this with this with this with this. Let's see how much we get. 1461902 multiplied by 0.1413 multiplied by 1 multiplied by 0.00067. How much are you getting? $139. I'm also getting 139. I'm also getting 138.4 something. But I see a different answer here. Let's recheck our calculations. I is EB by pi, that is sigma t power 4 by pi, 5.67 10 power minus 8 into 3000 power 4 by pi should be correct. Area H equal to pi d into W. Yes, that is correct. Where D, okay. This is not D, right? I should multiply it by a factor of 2, right? This is only radius. So I should multiply this by a factor of 2. So this is into 2. Zero point 2826 meter square. So this also will get multiplied by a factor of 2. Did you understand the mistake that we made? 276.8. Did you get what we did wrong? Why we need to multiply by 2? Yes, because we are doing here pi times d times w, right? Pi dw, the circumference into that width. But when I wrote here this L sin 30, that is only the radius, not the diameter. So the actual d value is 2 times this radius, 2r. Is that clear? Yeah. Okay. So that was all about that question. Take a minute to go through the problem and the solution, and let me know if something is unclear in this part. Is everything clear?
Yes, sir.
Okay. Bala, it's okay, right? Yeah. That's all what I had for today's session.
Yes, sir.
Yeah, that's all what I had for
Thank you, sir.
today's session. With that, I will close today's session. And for Bala, I will check problem 3
Yes.
from assignment 10, and I will reply back to you.
Thank you, sir.
Thank you very much.
Okay.
Very good session, sir.
Yeah, thank you for attending the session. Good night. Thank you.
Good night, sir.
Bye.
Good night, sir. Thank you.
Yeah.